Okay, so I'd like to talk about validating artificial intelligence. Although actually from the discussion yesterday, I realized that validating with artificial intelligence is actually just as important a concept. So thank you, Tom. I think there are some really practical ideas that I'd like to discuss, or rather introduce really, because a lot of this is just getting started, as ways of making these traditional system safety processes more efficient. So, for the past 10 years now or so, I've worked in the middle of those two arrows on some very interesting projects. So, although I've been at Carnegie Mellon for some time, I like to think that I have a little bit of experience as a practitioner doing things where I'm taking at least unmanned systems and trying to develop them in ways that are safe. So I've passed unmanned ground vehicles through Army safety programs. We've tested autonomous Army and Navy programs before. And one thing that I see is that these two cultures are currently separate. And I think that activities like this meeting are actually very important to try to bring these ideas together. So for instance, the AI community could benefit from experience thinking about things like hazard analysis. We've heard that term brought up a couple times in the talk so far. Yeah, thanks, Alwyn. And building assurance cases. These are some common ideas that I think actually are perfectly natural and you can get a lot of benefit out of. On the other hand, the dependability community I think can benefit tremendously from artificial intelligence and machine learning to try to improve the efficiency of some of the techniques that we have established for a long time. So, but what I'd like to talk about today is one piece of that, because there's lots of different angles here, and that piece is validation. So whereas verification is the process of making sure a component has satisfied its specs, and I hope that component has a spec, which is often something that we run into. Validation is about showing that the spec is suitable in the first place. And that's important, but it's very hard using traditional safety engineering approaches. And I think primarily the thing that's interesting to me is that it's hard because there are unavoidable ambiguities in the requirements that we try to place on these systems. And we've done this for different kinds of components before, and it's always the perception that comes in really, really challenging here. You can use a lot of existing techniques to take this kind of an approach where you define requirements and then synthesize the design from that and then implement according to the design. You can do that for a controller, a planner, something like that. But it's actually very difficult to place a requirement on a perception system. So again, just to introduce this idea, which is essentially the process that is mandated by system safety processes, is that first we elicit requirements, and as I said, then we synthesize designs from these requirements, and finally we implement according to the design. And I draw this process, it's not usually from bottom to top, but because I'm trying to place emphasis on the requirements portion of it, because that's the bedrock on which a safe system is built according to these standards. And so then the other thing that we need to do in these traditional processes is then sort of verify that each level satisfies its foundations. So an implementation has to satisfy, or has to be built according to the design. The design has to satisfy all the requirements. And verification is very important here. And in some cases, verification can find things like conflicting requirements, but it's also very common to see that dangerous gaps or ambiguous requirements or missing requirements can be uncaught through this whole safety process. Okay, so how do we go through and make sure that we're not missing anything right now? Well, that's a very manually intensive process. You need to get domain experts in the room, and you need to spend a lot of time reviewing things like hazard analysis. So go through and come up with what kind of problems you're trying to avoid, and that's the scope of your whole safety program there. You can look at prior programs and see what things went wrong on those programs and try to apply them to your current task. But then we can ask how effective that sort of approach is when you're doing something very novel, which I think is important here because we're talking about really applying new applications, new technologies, and making them safe. So there's almost a fundamental limitation there. So let's take as an example the idea of pedestrian detection. Okay, this is, I think, a very interesting and of course, very realistic capability that we want autonomous vehicles to be able to perform reliably. So how might we try to validate requirements for pedestrian detection that would be used by an autonomous car? How would we, what basis for these requirements might we have, and how might we try to prove that those requirements are sufficient? Well, so first let's start with a high-level requirement. This is often how it's done. You start with sort of your safety goals, and then you try to break them down. Your high-level requirement might be that we're going to use pedestrian detection to try to stop the car before it approaches a crosswalk. Okay? And then we try to break this down into more detail. The first step of that, and again, I'm not using any formalisms here, but I think we can start to think about this in terms of the different, maybe the nouns that we have, right? And so these different concepts, we want to try to refine what it means for, and I don't mean refinement in a formal way, but we want to refine what it means for the car to stop. We want to refine what it means for there to be a pedestrian present, and what constitutes a crosswalk, right? We want to make this all as strict as we possibly can so that we can test it and so that we can verify it. So refining the concept of stop is something that's traditionally done. This is not the most challenging case that we're talking about here. You would want to define bounds on how quickly we must come to a stop. Again, mostly to support testability, because you want to test Oracle to be able to say that we've successfully implemented the stopping capability properly. And then, of course, we probably want to allocate stopping responsibility to different design components, right? So you have, you talk about how you're measuring speed when you're coming to a stop. You talk about your redundancy approaches and what kind of techniques you're using to cross-check that speed so that you can trust it. And again, this is all validated through, again, mostly formal review, right? You're looking at a bunch of experts who have done this kind of thing before. You have them take a look at the techniques used, and you have them constructively criticize them. Maybe you trace some of these decisions back to safety tests to say that certain bounds are appropriate for the application, things of that nature, right? So you're breaking this down. But then when we try to break down these other terms, we run into problems, okay? So what does it mean to be a pedestrian? Well, do we define it by a geometry? Do we define it by some other appearance, right? I've actually seen safety standards that go in and try to do this by defining a common shape of a person. And you want to make sure you have a testing plan that's mandated by the standard that says, make sure that your perception system can find a barrel, and usually the barrel is, I'm going to do that. Usually the barrel is, the size of a child, and it's got a particular geometry, and it's got a particular color. In an agricultural setting, maybe it's a matte green for some reason, right, to make it the hardest possible thing to pick out from background vegetation. And then the standard says, well, test that you find that, n out of n+1 times, and there you go, right? But we really don't believe that that's suitable here. If we had a magic sensor, we'd be able to do the same kind of thing that we can do with the term stopping. If we had a sensor that could unambiguously detect any pedestrian, or even better, a pedestrian in a crosswalk, this would be a fairly easy job for us. And in fact, in some requirements, us safety guys try to impose operating constraints, right? So if you're talking about not just pedestrians, but people on a factory floor, you give them beacons or markers or something like that, and just to make it easier to define what it is that you're talking about. And the reason why this is all such a challenge is that, really this is the fundamental problem that robotics has been dealing with since its inception, right? Is how we unambiguously define these things that we just don't have ways to, to fully define, right? If we could take unambiguous mathematical logic and define the geometry of a pedestrian, we wouldn't be using machine learning, right? We use machine learning because we don't have that capability. And it's actually amazing that machine learning works out so well despite that fundamental limitation. And one example where it actually works fairly well is using probabilistic methods like supervised learning to pick out pedestrian detection, right? So if you look at a lot of vision-based approaches to pedestrian detection, you'll see that some kind of supervised learning is involved. So just as an example to sort of step through how we would try to validate this, I want to take a look at one approach. There are lots and lots of approaches, but one approach that I think is particularly interesting is called deformable part models. And deformable part models, easy for me to say, attempts to fit a model of how limbs can move on a human body to try to find people in different poses and postures, right? Because you might see them from different perspectives, or they might be walking, or things like that, right? So you take a lot of labeled examples, and then you build a model like this. So here we have 3 different models, and again, there are lots of different results that you can look at the literature on how this works. Some of them work differently, but basically you typically have one pass where you have a model that's been fit to an overall human, and you sort of get some idea of a human shape there. And then interestingly, you also have models that are fit for each of the parts. Okay, so you can kind of see the head and the arms and the legs. The interesting thing to me is that there's a third model that's learned, which is the distribution, the expected distribution of the limbs on the body itself. Okay, so this is where you get the ability for arms to move around, or legs to move around, or different human shapes and sizes, different postures, different poses, things like that. So then once it's out in the field, of course, the algorithm scans images that it hasn't seen before, tries to find the people, and it works great, typically. How great does it work? Well, that question is usually answered using some sort of receiver operating characteristic, right? It's a trade-off of false negatives versus false positives. But it's not really that there's one way to make that trade-off, right? You want to make that trade-off based on your application. So depending on what you're doing, so now again, you have to think about the hazards that you're trying to mitigate against and what your safety case. It might be that you can accept false positives in this application, shown here in red, because basically a false positive in this case would cause the car to stop in too many crosswalks, right? And maybe that's an acceptable trade-off for safety, because at least you're still safe when you make that kind of mistake. You're just not available, as we would call it, right? Your system stops working more often than you want it to, and then fewer people buy it, right? But at least now our safety case is separated from the underlying performance of the system, and that's a common sort of trick that safety engineering tries to use. But it's not really the ROC curve and these kind of trade-offs that safety engineers are most worried about. We believe that we can spend a lot of time and money and technology on driving down these kinds of failure rates, right? Right now a pedestrian detector may have 2 nines of reliability, or and you may want to push it to 4 nines of reliability using some tricks, right? But it's really not that trade-off that causes us heartburn. What causes us heartburn is the reason why we have uncertainty here. Okay, so it's not laziness. If it's a safety issue, we will not be lazy about it. It's this ignorance. Okay, and I don't mean that negatively. It's just, again, we could not place requirements on what we meant by a pedestrian, so that applies an underlying kind of ignorance that we have to deal with. Okay, so we can use traditional safety techniques, but they won't make partially observable environments fully observable. Right? They're not going to make non-determinism deterministic. If centuries of epistemology have taught us anything, it's that we're always going to have these limits of ignorance, and we're going to have lack of theoretical models that go along with any pattern that we find in our data. Right? We're going out and fitting these deformable part models to the examples that we've seen. We don't really have an explanation for why those models are well suited. And that sort of cuts right to the heart of the question of the fundamental safety of our pedestrian detector. So again, I think that if we want to look at this from a safety engineering point of view, we don't care as much about the detector's performance on test data and more on the suitability of the detector's underlying assumptions. We've just come through a section on formal methods, and a very important aspect of formal methods are the assumptions or the proof obligations that are placed when we use different kinds of models in different kind of contexts. And I think we want to be thinking the same way here, right? The problem is these underlying assumptions aren't always discussed Certainly they're not discussed in discussions, in the academic literature necessarily, but they need to be when we are talking about them in the context of safety. So how do we do this? From the discipline of safety engineering, I think we should draw on the concept of what's called argument structures, which try to make explicit these kinds of assumptions on which we're making a safety argument. So argument structures form the basis of safety cases for a lot of fielded systems today, right? Fighter aircraft, rail, air traffic management, lots and lots of different systems. There are standard ways of doing this. There are standard notations that people are trained to use. And I think that I think that they're very useful in this context. We should say that we're not trying to use these structures to tie together deductive inferences. We're trying to take our argument, our practical argument, and lay it all out as best we can. Okay? So a classic framework is from Stephen Toulmin, and he uses this idea of a warrant, okay, which is a justification for moving from an observation to a conclusion, which actually sounds a lot like our model that we've developed, right? Why do we believe that there's a pedestrian present? Well, because we've developed this model. And the interesting thing about the idea of a warrant is that warrants are, again, never completely principled. They're appeals to some sort of societal decision or some sort of experts or things like that. And in this case, we're appealing it to the data-driven nature of this model that we've learned. Okay? So I guess one warrant is that our current model is suitable, but actually a more general warrant would even be that there is a suitable deformable part model that is available across this whole population of pedestrians, which is, I think, an interesting question to ask too. So unfortunately, these warrants won't always hold, and won't hold when this gentleman comes out into our crosswalk, right? So we try to fit him to our pedestrian detector, and we see that there's just fundamental differences, right? And we know that historically, this is the situation where our safety accidents will occur, right? Where these underlying assumptions just don't hold. So since perfect knowledge is unattainable, I assert that AI and safety would actually benefit from being able to find these cases as efficiently as possible, right? So this is an adversarial approach to validation, which might be unsatisfying to those in the safety community because it never actually reaches a conclusion. There's no way to determine that it halts. But nonetheless, it's actually extremely efficient, right? Because we can use, if we can find a way to automatically generate test cases that come up with ideas that look like this, then we can find gaps in safety requirements. And really what this helps us look at are these unknown unknowns, or also referred to as a particular color of waterfowl. The interesting thing about this, I won't spend much time on this slide, is that actually all automation suffers from these kind of problems. So we can take these ideas and feed them back into existing safety cases, right? If we had an automated way to come up with situations where even these well-founded, dependable systems, fail, that's maybe a gap that the sort of manual examination just hasn't found, right? Okay, so there are techniques that I think are really interesting to look at from this perspective. This idea of inceptionism, which there are several interesting examples of. This one is actually from the Google post that you've probably all seen. A deep neural network has been taught to classify pictures of dumbbells. Okay, and so the interesting idea that was discussed in the literature is that, hey, look, you can get it to represent pictures of dumbbells. But I think that's cool. But the interesting thing from a safety analysis perspective is that a human can look at the that's validation. Okay, so we know that it's learned the wrong thing because every picture of dumbbells that it produces has an arm attached to it, right? Similarly, we can use adversarial test cases to generate examples that look like baseballs, and again, it hasn't learned that baseballs are round. So these are semantically interesting test cases that we can fold back into the learning process, right, to improve the system. And I think that there's a very, very strong analogy here with the way these safety processes work. But what I'm trying to advocate for is to dramatically accelerate those kind of loops, right? So use these kind of data-driven approaches, use these automated approaches to come up with these counterexamples, and then have the safety expertise, all these smart humans, think about sort of how to generalize those cases and improve the underlying assurance case. So I'm going to try to keep time here as best I can. I can talk about this sort of stuff all day. Thanks for your attention, and look forward to any questions later.